Hey everybody, in this video we are going to do some FRQ questions from the AP Chemistry FRQ section, and these are going to be easier than most of the multiple choice questions that we did for the multiple choice video I made for enthalpy. So the very first part states that the enthalpy change in a chemical reaction is the difference between energy absorbed in breaking bonds in the reactants and energy released by bond formation in the products. Okay, so that's just stating that when you break bonds, energy is absorbed, and when you make bonds, energy is evolved. Alright, so let's look at our reaction. N2 plus 3 moles of F2 makes 2 moles of NF3. The delta H at 298 degrees Celsius is negative 264 kilojoules per mole. Now, 1D says how many bonds are formed when 2 molecules of NF3 are produced according to the equation in the box above. Okay, well in the box above it says 2 moles, or you can read it as 2 molecules of NF3 are produced. So how do you draw that? Well, NF3 looks like this. And there's a lone pair over here, and there are lone pairs all around the fluorines. And it kind of looks like that. And if there are 2 of them, and there are 3 NF bonds in each of them, then there are a total of 6 bonds. And more specifically, it's going to be NF3 bonds. So the answer for D is going to be 6 bonds. Now, let's talk about E, using both the information in the box above and the table of average bond enthalpies below to calculate the average enthalpy of the FF bond. So let's try doing that. So over here, let's just draw all 3 Lewis structures. So 1 mole of N2, which looks like that, and we are combining it with 3 moles of FF, and these will have lone pairs on them, and it becomes 2 nitrogen trifluorides. So it looks like that, and the lone pair there, and there you go. These are the Lewis structures. Now let's see how many bonds are broken and how many bonds are formed. So 1 mole of NN triple bonds are broken, 3 moles of FF single bonds are broken, and on the right hand side, 6 moles of NF single bonds are formed, since 3 in each moles and 2 moles, so 6 moles of NF single bonds. Now let's do the summation for these bond enthalpies. On the reactant side, they will all be positive since we're breaking bonds, and breaking bonds takes energy. So, on the left-hand side, the bond enthalpy for NN is going to be 946. So 946 plus 3 times the FF, and that's an unknown, so we could put a question mark there. And we have to add it to the products now. Now for the products, we have 6 moles of NF bonds, and each NF bond has a bond enthalpy of 272 kilojoules per mole, so 272. But remember that bonds are being formed, so this should be a negative number. And these are the positives, and this one is a negative. So adding this all together, it has to equal the net enthalpy for the reaction, which is negative 264. So negative 264. And doing the math, we have to simplify this first. So 946 plus 6 times negative 272. We get that negative 686 plus 3 question mark is equal to negative 264. Now moving things around, negative 264 plus 686, we get that 3 question mark is equal to 422, and divide everything by 3, and we get that the question mark is equal to 141 kilojoules per mole, and this is equal to the bond enthalpy for the FF single bond. So that would be your official answer. And note that you have to keep track of your sig figs. Since there were 3 sig figs here and 3 sig figs here, your final answer should have 3 sig figs. And the 3 doesn't count as a sig fig since there are exactly 3 moles of FF single bonds in 3 moles of fluorine gas, and because it's an exact number, it has an infinite amount of sig figs. So let's move on to the next FRQ. So a student investigates the enthalpy of solution for 2 alkali metal halides, LiCl and NaCl. In addition to the salts, the student has access to a calorimeter, a balance with a precision of plus or minus 0.1 grams, and a thermometer with a precision of plus or minus 0.1 degrees Celsius. To measure the delta H solution for lithium chloride, the student adds 100 grams of water initially at 15 degrees Celsius to a calorimeter and adds 10 grams of lithium chloride, stirring to dissolve. After the lithium chloride dissolves completely, the maximum temperature reached by the solution is 35.6 degrees Celsius. Okay, we have a bunch of information. Now, let's look at A1. Calculate the magnitude of the heat absorbed by the solution during the dissolution process, assuming that the specific heat of the solution is 4.18 joules per gram degree Celsius. Include units in your answer. So what the student basically did is that the student has 10 grams of the lithium chloride, so 10.0 grams, and they put it in 100 grams of water. And when they combine it, well, let me put a decimal place after the 0 to keep track of sig figs. After they combine it, they actually get a solution, and the solution is 110.0 grams. And the reason being is that the solution contains 100 grams of water and 10 grams of the lithium chloride. So the solution would overall weigh 110 grams because the conservation of mass says that when you combine 2 things or whatever you do to something, the mass will remain constant and it won't be created nor destroyed. So the solution will have 110 grams total. And it says that the temperature was initially 15.0 degrees Celsius, and it went all the way up to 35.6 degrees Celsius. This tells us that this reaction is exothermic, and the delta T is going to be 35.6 minus 15, which is 20.6 degrees Celsius. Now, what other information do we have? Well, we have the C, the specific heat, which is 4.18 joules per gram degree Celsius. So we can use Q equals mc delta T to figure out the magnitude of the heat absorbed by the solution. So the heat absorbed by the solution will be mc times delta T. So Q of the solution is equal to the mass of the solution, 110.0 grams, times the specific heat for the solution, which is 4.18 joules per gram degree Celsius, and the delta T is 20.6 degrees Celsius. And notice that your units cancel out and you're left with joules. So 110.0 times 4.18 times 20.6, and we get that the heat absorbed by the solution is going to be, let's see, 3 sig figs for our final answer, so 9.47 times 10 to the 3rd joules, and this would be the correct answer. And this would be the answer for 2A1. Now we have to look at 2A2. Let's ignore that 1 there. So 2A2 says, calculate the value of delta H of solution for lithium chloride in kilojoules per mole of reaction. So now we have to find the amount of heat that is released by the reaction in kilojoules per mole of reaction, so for 1 mole of lithium chloride. So how many moles of lithium chloride did we add to the solution? So we have to take 10.0 grams of lithium chloride and divide it by the molar mass. The molar mass of lithium chloride is, well, let me check it out, 6.94 plus 35.45. The molar mass is going to be 42.39. And in the end, we get that we have, let's see, we have about 0.236 moles of lithium chloride. And before we continue, we have to think about what the question is asking. It's asking for the delta H of solution. Now, in 2A1, we calculated the amount of heat the water absorbed, but don't you agree that the amount of heat the water or solution absorbed is equal to the negative of the heat released by the reaction? So what I mean by this is that the Q of the water will be 9.47 times 10 to the third joules, but the heat that the water gained is the amount of heat that the reaction released. So it would be negative Q of reaction, and thus the Q, or the heat of the reaction, is going to be negative 9.47 times 10 to the third joules. And this makes sense since the reaction was exothermic because it heated up the water. So that means that the reaction must have a negative sign for the heat, or the delta H. And if we remember, delta H is equal to the amount of heat per mole. And we could simply plug and chug, so negative 9.47 times 10 to the third joules per 0.236 moles. And doing the math, we get, well, let's see, 9.47 times 10 to the third divided by 2.36. We get about 4.01 times 10 to the 4 joules per mole of lithium chloride as the delta H naught of solution. Now, we have to do this in terms of kilojoules since the question wanted it in kilojoules per mole of reaction. And, let's just put it in the units that they want. So we're going to do it in terms of moles of reaction. And we have to convert this to kilojoules. So just subtract 3 from the exponent and we get this. And this would officially be the answer for 2A2. So before we move on, let's read this explanation. To explain why the delta H of solution for sodium chloride is different than that for lithium chloride, the student investigates factors that affect the delta H of solution and finds that ionic radius and lattice enthalpy, which can be defined as the delta H associated with the separation of a solid crystal into gaseous ions. So, for example, lithium chloride solid becomes lithium plus not aqueous, they said gaseous, so we have to put a gas plus Cl minus gas. Now, notice how in the video about the types of enthalpies, we said that the lattice enthalpy was the opposite of this, and that's fine because if they define what the lattice enthalpy is, let's just follow what they say, no matter what we know, because what they tell you is ultimately what you have to apply. So let's read on. The student consults references and collects data shown in the table below. So lithium plus has an ionic radius of 76 picometers and Na plus has an ionic radius of 102 picometers. Now B says, write the complete electron configuration for the sodium plus ion in the ground state. So it would be 1s2, and let's find how many protons Na has. So Na has 11 protons, and it would have 10 electrons since it has a +1 charge, or an excess of 1 proton. So 10 electrons, let's do this. 1s2, 2s2, 2p6. That's a total of 10 electrons, and that should be the right answer. C. Using principles of atomic structure, explain why the sodium plus ion is larger than the lithium plus ion. Well, lithium plus has an electron configuration of 1s2, while sodium plus has that electron configuration. And notice how the valence electrons in sodium plus are much further from the nucleus than those in lithium plus, and that's because the valence electrons in sodium plus are in the 2 principal energy level, while the lithium plus has its valence electrons in the principal energy level of 1. And because of that, sodium will have a much larger electron cloud than lithium plus and thus be larger. Now, let's take a look at D, which lithium chloride or sodium chloride has a greater lattice enthalpy. So their definition of lattice enthalpy is the energy it takes to break the ionic bond to form the gaseous ions. Now, which one would have the greater lattice enthalpy? It would be the one that would take more energy to break. So let's draw lithium chloride and sodium chloride. So lithium chloride is, of course, smaller because lithium is a much smaller ion than sodium is. And let's draw their centers. Their centers are over there. And notice how the bond length, or the distance between the 2 nuclei of the ions, is much smaller than the bond length of sodium chloride, which is much greater. So this is the greater one, that's the smaller one. And because this has a smaller bond length, and this is definitely due to the fact that lithium plus is the smaller ion, and because the bond length in lithium chloride is smaller than the bond length in sodium chloride, according to Coulomb's law, the shorter distance will cause a greater attraction in lithium chloride as opposed to sodium chloride, and because of that, the greater attractions between the 2 ions in lithium chloride will cause it to be harder to break the bond apart, which contributes to a greater lattice enthalpy for lithium chloride. And I will have an answer in the next slides, but for now, just listen to what I have to say. Now, E. Below is a representation of a portion of a crystal of lithium chloride. Identify the ions in the representation by writing the appropriate formulas Li plus or Cl minus in the boxes below. So we have a big circle and a small circle. So the question is Li plus the small circle or Cl minus the small circle? Well, if we think about this, if we compare the 2 sizes, we know lithium is in period 2 and chloride is in period 3. And things that are in lower periods are typically smaller. So I would argue that lithium would be the smaller of the 2, and chloride would be the bigger of the 2. And again, you could also look at their electron configurations and see that the valence electrons for chloride are in a much higher principal energy level than the valence electrons in lithium plus, and because of that, chloride will be a bigger anion in terms of size and ionic radius. So let's take a look at the answers now. So for 2A1, it was 9.47 kilojoules. For 2A2, it was negative 40.1 kilojoules per mole of reaction. For 2B, 1s2, 2s2, 2p6. For 2C, I wrote an explanation out. Na plus's valence electrons have a higher principal energy level than lithium plus's valence electrons, since electrons with a higher principal energy level have electron densities that are typically located farther from the nucleus. Then Na plus will have a larger ionic radius and thus be larger than Li plus. So instead of saying electron density, you could have said maybe an electron cloud that was larger, I guess. Yeah, that works too. And for 2D, I wrote a long explanation. So I said lithium chloride has the larger lattice enthalpy. Yeah, that's what it was. So the lithium plus ion is smaller than the sodium plus ion. So according to Coulomb's law, since the bond length between Li plus and Cl minus is smaller than that of Na plus and Cl minus, the ions in LiCl will be more strongly attracted. Therefore, the lattice enthalpy for the lithium chloride will be greater since it would take more energy to break the lithium chloride ionic bond. So this is my 1 or 2 sentence explanation, and I think that we're done. So thanks for watching. Have a nice day.